It's time for another amazing chemistry video with Mr. Stapleton, proudly sponsored by Farmers Union Nice Coffee.
Hi guys, this is the final part for topic 2, which is managing chemical processes. This is just going to be all about optimizing production, so hopefully it won't be too long. It's really going to rely upon you having a good understanding of rates of reaction and equilibrium for the first part of this topic, because that's really what comes in with industry. So if we're talking about industry, there are 3 main factors that influence the production of chemicals, and in reality for industry it's no surprise that it really comes down to money and cost. Okay, what they want to do is maximize the rate and the yield while minimizing the cost. So the rate is how fast they produce their product, and the yield is how much of their product they produce. Okay, so it makes sense that if you're producing something, you want to do it as quickly as you can, produce as much as you can, and do it for as little as you can. And so what you're going to be looking at is things that affect the rate of the reaction. So you're going to be looking to maybe increase the temperature or increase the pressure or the concentration, something like that, which will increase the rate. But you're also going to do something in terms of the equilibrium within the system to increase your yield, to maximize your forward reaction and the concentration of your products as much as possible. So you're going to need to bring in the Chatelier's principle and talk about the shifting to an equilibrium when you counteract it. So, like I said, basically, when you are in industry, you want to maximize the rate and minimize the cost while maximizing the yield as well. One of the things that's a big factor is the type of metal that you need to extract. The type of metal you need to extract from the ore. That'll really be picked up in topic 4. Okay, so we'll look a little bit more around electrolysis and the different types of metals and how you extract them from their ore. But you just got to know if you need to use electrolysis for it, it's very expensive. Okay, and that increases the cost quite a lot. So if you can get away without having to do electrolysis, particularly of the molten salt, that'll minimize your cost as well. So, chemical industry, here's just an example. This is a map of copper within South Australia, okay, and you can see here some of the major copper deposits, okay, which are the big circles, and you can see where some of the copper mines are. Now, when you're setting up your mine, or your plant, I should say, for extraction of the metal, you want to consider a number of things. One, you want to think about availability of raw materials, which is why you can see that the major copper mines we've got set up here, okay, are where the majority of the copper resource is, but the actual factory to extract the copper from that might not be at the mine, because some of the other things you need to think about are the ease of handling and transporting the chemicals, the value and demand of any byproduct. Byproducts are things that are made in a reaction but are not the desired product, but they might have some actual value. Okay, then you might want to think about any environmental concerns, and the other thing is about availability of a workforce. Okay, so you can see some of these ones here. They're built near Cooper Pedy and near Gawler, you know, out this side of Adelaide. There's still quite a ready workforce there. But if you were going to, if you found a massive deposit somewhere out in the middle of a desert, for example, you wouldn't want to build your factory there, because you'd have to house all the people. Or you'd have to allow and pay them to travel long distances. So you really have to think about all those sorts of things before you actually build your plant. These are just some definitions. So we went through about raw materials, so starting materials that others can be made from. The ore is an impure mixture, usually with a metal, that we extracted. So some examples are like zinc blend, hematite, magnetite. There's different types of different ores which we get a metal from. One that people often struggle with is feedstock, and that's the materials that we use to make chemicals. Okay, so in a specific reaction, if you're looking at a chemical reaction in industry, the reagents that you use, the reactants, are the feedstock. Now, they may come from raw materials. So a really good example is that air is a raw material. Okay, so that's what we use as our starting product. From that, we extract nitrogen in the Haber process, and that is the feedstock. Okay. We've also got waste products. They're things that, like it says, they're waste. We can't use them. They're not viable, so we can't sell them. Then there's byproducts, which can be quite useful. So I'm going to just look at 2 reactions reasonably quickly, and looking at how we apply some of these terminologies, but also looking at how we maximize the rate and the yield while minimizing the cost. So the first one we're going to do is look at the Haber process here. So the Haber process is used to produce ammonia, and we've got our equation here. It's nitrogen plus hydrogen to give ammonia. We get a delta H value of minus 92 kilojoules per mole. So hopefully you've got a bit of understanding about enthalpy. A negative enthalpy value implies that the reaction is exothermic, so energy exits the system. So straight away when you see a reaction equation like this, you should be starting to think about things that will impact on it. So an increase in temperature favours an endothermic reaction, so they'll obviously have a play here. Okay, you need to think about number of gaseous moles on each side and how that will actually impact it as well. So the question is, what could the manufacturer do to maximise the rate and yield of ammonia while minimising the cost associated with its production? So if you look at a flow chart, and this is one of the things that they want you to have a look at, so I'm actually just going to move me a little bit. There we go. Alright, so we've got a flow chart here, and they might very well give you a flow chart like this in the exam and ask you to have a look at it and decipher from it. So we've got nitrogen, which is our feedstock, from air, which is our raw material. We've got hydrogen, which is our feedstock, from methane gas, which is a raw material. We compress them together. So straight away, if you see compressor, you think increased pressure. Okay, so you have to think about what effect this will have upon this equilibrium. Okay, they come into a reaction chamber here. We use an iron catalyst. So again, you think catalyst, increased rate of reaction. You need to think about that. Okay, we have what's called a heat exchanger. We recycle the heat back into it. Okay, we get a condenser out. Now this condenser here is purely to liquefy the ammonia because it's much easier to transport gases as liquids. Okay, they take up far less space. The reason for that is 1 mole of a gas takes up 22.4 or 21.4 litres, something like that. So it's a reasonable amount as opposed to 1 mole of a liquid, which takes up much less. So the condenser here is purely to make it liquid ammonia. So we take the heat out of it, we turn it from a gas down to a liquid, we recycle the heat into the reaction. So we're obviously putting heat in, increasing the temperature, and any unreacted reactants are going back up here. We're trying not to waste anything within the system. So the question is pressure, where we're increasing the pressure here, temperature, where we're putting heat back in, presence of the catalyst. How will all of these maximise the rate and the yield while minimising the cost? Okay, so we have a look here. Alright, what we're going to do is I'm just going to move myself out of the way again, and what I'm going to do is try and get some drawing on here. Okay, so see hopefully if this is so pressure. You've got to remember we've got, so I'm just going to write the equation up the top here again. So we've got N2 plus 3 lots of hydrogen. And again, you guys, I'm sure you're loving my mouse writing and drawing by now. Gives us 2 moles of ammonia. Okay, so what we've got here is we've got 4 moles on this side because there's 1 mole of nitrogen, 3 moles of hydrogen in equilibrium with 2 moles of ammonia. Okay, so an increase in pressure is going to favour the forward reaction, that's the side with the less gaseous moles, and so that's going to not only increase the concentration of our reactants, because that's what increasing the pressure does, and that will increase the rate, but it will also favour the forward reaction, which will increase the yield. So the optimum condition for pressure will be a high pressure. Okay, so we're going to increase it, we're going to have a high pressure. Benefit to the manufacturer is going to have an increased rate because we're increasing the concentration. Okay, and it's going to have an increased yield, okay, simply because we're going to favour that forward reaction. Now temperature, you've got to remember that this forward reaction is exothermic. Okay, so what that means is an increase in temperature is going to favour the back reaction, okay, which is the endothermic. So as we increase the temperature, our yield of ammonia is going to decrease. So we don't want to use a very high temperature, but if we go for a really low temperature, what's going to happen is that the rate of the forward reaction, because it's equilibrium, the rate of the reaction, the formation of ammonia is also going to be very low. So the temperature we want to have is a low to medium temperature. I think they do it around about 450 degrees Celsius, which is relatively low for industry. The benefit of that is it's going to increase the rate, okay, because we've got a 450 degree temperature, and it's not going to affect the yield too much, okay. Look at that F, my goodness, not affect the yield too much because we're not favouring the back reaction too much. Okay, the presence, obviously, optimum condition is to have a catalyst, which we do. Okay, and that's going to increase the rate of reaction by providing alternative reaction pathway with a lower activation energy. Then you have no effect upon the yield. Okay. Now what you do need to think about with these is there going to be a cost associated to the environment. Okay, an increase in pressure, the effect on the environment is going to be negative basically. So it requires high energy to produce a high pressure system. High energy equals increase in CO2 emissions. Okay, so that's obviously going to contribute to the greenhouse effect. It's going to be a negative to the manufacturer in terms of you need specialized expensive equipment for an increased pressure, but in terms of the environment, the energy that you need to create that high pressure is going to be negative as well, because that's going to increase CO2 emissions. Again, for temperature, again you're going to need to supply energy into it, which again is going to increase your CO2 emissions. Luckily we're not using a massively high temperature though, because that's really not going to, 450 degrees is relatively low. It's not going to require too much CO2 burning or fossil fuel burning, so it's not going to be too bad. A catalyst, the effect on the environment really is nil, because the benefit of catalyst is that you only need a very small trace amount of the catalyst in order to increase the rate of a reaction. So that's really a benefit. Pretty much every chemical reaction industry uses a catalyst because there's very little downside. You increase the rate for a very small cost, and it's very beneficial. So what I've done here is I've basically just explained all of this. It's done at 200 pressures atmosphere, which is very high because that favours the side with the less number of moles. Okay, low temperature 450 degrees is favoured because the forward reaction is exothermic, and we use a catalyst to speed up the rate of reaction as well. Now if you want to calculate the what we call the yield of the reaction, okay, what you do is you use this little formula we've got down here, where the percentage yield is the actual yield, so this is how much you actually get out of it, over what we call the theoretical yield. So what you could calculate from your stoichiometry values, if you had so many moles of nitrogen, so many moles of hydrogen, what in theory, how much should you actually get of your nitrogen, of your ammonia, sorry. What happens in industry though is you never get 100% yield basically. That's why we do things like increase the temperature, increase the pressure to push it towards the product side. And what you can do is calculate a percentage yield based upon dividing the actual yield, how much you actually get, by how much you should get based on the stoichiometric values, and timesing it by 100. So in the exam they might give you the yield that you get, and maybe ask you to calculate theoretical yield and then a percentage yield. Okay. I'm just going to show a couple of other little flowcharts for you to have a look at. So zinc production. So this was in the chem curriculum last year as a major point. I think they're still probably going to put it in with some questions as well. There is a YouTube video here, fairly in depth on the zinc production, but you just need to get a flowchart like this. Have a look at things like, what are the raw materials, what are the feedstock, what are the conditions that are used, what things could they do to increase the yield and the rate of the reaction while minimizing the cost. So obviously what they've got here is they've got some byproducts and some waste products here. Okay, they've got electrolysis using, so that's going to increase the cost. Okay, they've got roasting over here, so obviously temperature or heat is being applied, so that's going to increase the rate of reaction. It's going to be negative to the environment. Okay, and they've got another product here of sulfuric acid being produced as well, with some waste products over here as well. So this one you don't actually get the equations on, all right? And this one it doesn't rely upon really gaseous reactants, so you can't really do pressure ones, but they do increase the temperature to increase the rate of a reaction, and obviously you could remove the zinc as it forms in electrolysis, but it's not really an equilibrium reaction, so that's not going to increase the yield either. The main thing about this one is just to try and see if you can identify different products from it, and maybe give some ideas about byproducts, waste products, and maybe some conditions like increased temperature. Other one I'm going to look at is the contact process, so I'm just going to move myself again. So the contact process is used to make sulfuric acid. So we've got sulfur burning in air to form sulfur dioxide. Again, you could look at increasing the pressure, and you're going to have an impact on this because it's 1 mole to 1 mole. Okay, but in this one here, SO2, there's 3 moles here in equilibrium with 2 moles, but they use 1 atmosphere pressure because it's only 3 to 2. It's not going to have much of an impact. Again, a reasonably low temperature, which probably implies this forward reaction is exothermic as well. They do use a catalyst, however. then you've just got this further flow chart where you get your final sulfuric acid as your product. There's not really any byproducts here. Your raw material is air, your feedstock is oxygen that you get in there, and you're also using sulfur as a raw material as well. No byproducts through here because you're trying to get your sulfuric acid as your final product. Okay, so hopefully you guys have got a good handle on this topic, in particular with rates of reaction equilibrium, because that all ties together when you come to this final section about understanding chemical industry. If you remember, you want to increase the rate and the yield while minimizing the cost, and you keep in mind those 5 things you need to remember when you actually build a chemical plant and where you're going to site it. Hopefully you'll be fine. Alright, as always, good luck guys. If you've got any questions, just leave them in the comments below. I'll answer them as best I can. Thanks guys.